So I've got a cold and I'm really annoyed, really annoyed because, well, I've got a cold and I need a wee. Anyway, this is the 2 clocks experiment again, right? Because obviously some people still think that 2 clocks experiment does what Einstein says it does. Right? Now, I was reading about electron size, the size of an electron, and see if anybody's actually measured the size of an electron yet. And it turns out that, and there's a scientist in America, I think, I can't remember which university it is, his name's Cummins, or Hunter, whatever his name is, I don't know. So anyway, I'm reading this article about electron size and electron magnetic moment, because they're trying to measure the magnetic moment. And the paragraph goes like this. This is what I pulled out for you. Scientists have thus developed a bag of tricks to maximise their chance of detecting an electric dipole moment. By watching the electron for as long as possible, by enhancing its reaction, and by removing any sources of outside error as possible, the work is finicky and frustrating. At Amherst, Hunter spent years fine-tuning an experiment with cesium atoms and produced a limit in 1989, only to be overtaken the next year by Cummins. That work at Berkeley looked for the electric dipole moment in thallium atoms in the wee hours of the morning, when nearby trains that could disturb the measurements were running. The work is finicky and frustrating. Let's do that one again. That work at Berkeley looked for the electric dipole moment in thallium atoms at the wee hours in the morning, when nearby trains that could disturb the measurements weren't running. Now, that last sentence, or last part of the sentence, when nearby trains that could disturb the measurements weren't running. So you've got an aeroplane flying through the air, right? It's got an atomic clock on board, and we've got these things called neutrinos, right, which we shoot from CERN. We shoot a proton into a graphite block. The graphite block catches the proton knocks off loads of subatomic particles. They're all travelling at above the speed of light when they finish. You can work it out through Cayley-Dickson algebras. And then you get a neutron beam, a neutrino beam, coming from CERN reactor, going down to Gran Sasso, whatever it's called, underneath a mountain in Italy, which is 700 and something miles away. And quite recently they've figured out that there's a possibility that these neutrinos are travelling faster than the speed of light. Now, they are travelling faster than the speed of light, guaranteed, but they're slowed down because they have to travel through atoms. They're travelling through rock, dense rock, and they get slowed down. That's why they've only measured them at about the speed of light, because through rock they'll only travel just above the speed of light. And they get caught by a massive mass lead detector. So you've got to imagine these neutrinos are passing through atoms. They're travelling through rock, dense rock, and they get slowed down. And then they reach this lead detector, and only a couple of them actually get caught in this lead detector. So you could make a uranium detector, couldn't you? Go on, make a uranium detector. How many more do you catch? You catch them all, but you don't catch them all. So your atomic clock, which was travelling at the speed of 700 miles an hour, faster than the one that's on the planet's surface, in a building. This one's in a aluminium cage, the one downstairs is on a building. Or was that in an aircraft? Fuselage. Doesn't matter anyway, because one was moving. And the likelihood of you catching a neutron when you're moving is going to be a higher probability when you're standing still. You're going to catch more when you're moving. And every single neutrino that hits the atomic clock core is going to slightly push it out, or slightly slow it down. And what happened was, the aeroplane that travelled around the planet and came back again had slowed down, and the one that stood still hadn't slowed down. And this is what I'm saying. As the aeroplane goes through the atmosphere, it creates charged particles. Each charged particle that it creates has a chance of creating a neutrino. So you're not only get the naturally occurring neutrinos, which are going to happen just because you're sitting on the planet's surface, travelling around the planet at the speed of the planet's rotation. When you actually fly on an aeroplane, you're in an electromagnetic fuselage, making neutrinos all the time. Not very many, but you're making more neutrinos than what would naturally occur, and they're right next to your atomic clock. So that really puts your atomic clock experiment out, doesn't it? Unless, of course, you work out the electromagnetic mass created around the aircraft as you're travelling through the clouds and the air and the moisture, and then exactly replicate that around the atomic clock on the planet's surface. And even then, you can't guarantee that you're going to get the same amount of neutrino contact centres, and they're the ones that slowed down the clock. So Einstein's wrong, Stig is right. It's going to be the unified theory of Stig. Do 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 do. Woo!